Right. So this is Math 1100, Exam 4 review. This covers bits of Chapter 6 and one section of Chapter 7. So 6.1, we learned how to find an antiderivative using integration by parts. So question 1, we need to find the antiderivative. Now the integration by parts formula, let me write it over here. Integration by parts formula says if we can write our integrand as u times dv, if we can somehow make it fit into u times dv, the integral of u times dv, then we can find the antiderivative by using the formula u times v minus the integral of v times du. So what we need to try to do in question 1 is choose which part of this expression is going to be u and which part of it's going to be dv. Remember the guidelines for u is something whose derivative becomes more simple. For example, if I choose x there for u, then its derivative du is 1, which is more simple than x. So if this is u, that means this has got to be my dv. So dv is e to the negative 3x dx. So what that means, that's a dv. So what that means is I have to find v by taking the integral of this expression here So in order to find the antiderivative of e to the u, right now we're going to use the formula e to the u du to find this integrand right here. So if this right here is u, if u equals negative 3x, that means the du is negative 3 dx. So I've got the dx, but I'm missing the negative 3. I'm supposed to have a negative 3 right here, which means I need a negative 1/3 out in front. And then I can finish this. The antiderivative of negative 3 e to the negative 3x is just e to the negative 3x. And then I've got that 1/3 in front there. So v equals negative 1/3 e to the negative 3x. So I've got my v, I've got my dv, and over here we had u and du. So I think we're good to go. We've got everything we need. So now the original problem, the integral of x e to the negative 3x dx, since I can now say that I can write this as u dv, we can use integration by parts formula, which is u times v. So x times negative 1/3 e to the negative 3x minus the integral of v. So that's this expression. Now since it has a coefficient, the negative 1/3, I'm going to write that in front. And then e, so there's v times du. Du is just 1 dx. And the only part left to simplify in this problem is this, which we have actually already done right here. We already did that problem. The integral of e to the negative 3x is negative 1/3 e to the negative 3x. So this expression here, I can just multiply the x and the negative 1/3 to negative 1/3 x e to the negative 3x. Here a negative times a negative is positive. And then the integral of e to the negative 3x is, remember, negative 1/3 e to the negative 3x. So final answer, we can multiply the 1/3 and the 1/3 to make negative 1/9. So there's your final answer. Question 2 starts the same way. We need to first recognize that this is integration by parts. So we need to choose a u and a dv. Now in the last problem we chose an x as a u value because its derivative was more simple. But oftentimes when you're doing integration by parts, if there's a natural log involved, it makes sense to choose that as u. Because when you find the derivative, it's 1 over 4x. Remember, the derivative of natural log is 1 over u times du, so the derivative of the denominator there is 4. So the derivative is 1 over x dx. So there's our u. So if this is u, that means that the x dx, that becomes our dv. So dv equals x dx. Well, that's an easy one. The antiderivative of x is just x squared over 2. So let me write that again. That means that v equals x squared over 2. So we've got v and dv, and then we had u and du. So we got to check that everything's covered. This was u, and then these two parts were dv. There's nothing extra or left over or unaccounted for, so we can write that as u times dv. So we're ready to use integration by parts. The integral of x times the natural log of 4x is equal to u times v minus the integral of v. Now v, x squared over 2 can be thought of as 1/2 x squared, which is a coefficient of 1/2. So I'm going to put the coefficient there, and then have the x squared in there. So there's there's v times du. Remember, du is 1 over x dx. And then this x squared times 1 over x is the same as x squared over x, which is just x. So this is natural log of 4x times x squared over 2 minus 1/2 times the integral of x. Now the antiderivative, or the integral of x, is again x squared over 2. So we've got natural log 4x times x squared over 2 minus 1/2 times the antiderivative of x, which is x squared over 2. So there's our antiderivative. For question C, or 3 rather, question 3, remember it makes more sense to not use radicals but rational exponents. So this is really x times x minus 3 raised to a power of 1/3. Let's look at it that way. So let's go ahead and choose x there for our u. Leaving du to be 1 dx. That means what's left over, the x minus 3 to 1/3. That's our dv. So when we try to find v, that means we need to find the antiderivative of x minus 3 to the 1/3. This is just an example of the general power rule, which is u to the n du. So here's u is x minus 3. So if we're going to use the integral of u to the power of n du, that means we have to have an inside function, which we do, and then we have to have the derivative of that inside function. Now the derivative of x minus 3 is 1 dx, which we have right there. So everything we have is there. We don't need anything extra, no extra coefficients or anything like that. So just apply the general power rule, which is adding 1 to the exponent there. So 1/3 plus 1 is 4/3. So we're going to get x minus 3 to the 4/3, and then we either divide by 4/3 or in this case multiply by 3/4. So there's v. So the original problem, the antiderivative of x is x minus 3 to the 1/3 dx equals u times v. So x times our v value here minus the integral, and since v has a coefficient, again I'm just going to write it out here, so 3/4 and then to a power of 4/3. So there's v. Now we need du. Du is just 1 dx. So simplifying here, the 3/4 times x, that's just 3/4 x. And then that x minus 3 to the 4/3, it's another example of the general power rule, u to the n du. So we're just going to add 1 to the exponent. 4/3 plus 1 is 7/3. So we got this 3/4 as a coefficient, and then we have x minus 3 to the 7/3, which means we're going to multiply by 3/7. And then I think we can finish it up. 3/4 times 3/7 is 9/28. All right. Now we're calling this one 6.2. However, in the 10th edition of the UVU edition of our textbook, in the back, in the appendix, it's really labeled as section 8.1. And it didn't really introduce a new technique of integration. Ultimately, what it boiled down to usually was just using the integral of du over u, which is natural log of u. But what we had to do first is simplify the expression that we started with using a technique called partial fractions, decomposing into partial fractions, which is a technique that a student would learn in a 1050 course. So I'm not even going to bother yet with the antiderivative part of this. I'm just going to look at this expression and try to break it down into smaller separate fractions. So first step is to factor the numerator. So we're going to have an x minus 5 and an x plus 1. And because we have two factors that results from the denominator, that means we're going to have two partial fractions. And then the next step is to multiply the entire expression by the lowest common denominator, which is x minus 5 times x plus 1. And then this common denominator needs to multiply each of the fractions. And when it does, the denominators disappear. So what you end up with on the left side is 4 equals a, and now on the right side you're going to have a times x plus 1 plus b times x minus 5. Now what we're solving for is a and b. We need to find out the values of a and b. What that means is it doesn't matter the value of x. X isn't the variable that we're solving for, so in an expression like this, when that's the case, you can let x equal whatever you want. The technique involved here is called choosing convenient values. See, if you only have one equation but two variables, it makes it hard to solve for both variables if you have one equation. So what needs to happen is we need to cancel one of these variables. For example, if I let x equal -1 and then I plug it in for that x, -1 plus 1 is 0. 0 times a is 0. So a disappears, allowing me to solve for b. So if I let x equal -1 in for both of these x's, the equation now becomes 4 equals, and then -1 here, minus 5 is -6, so -6b, which means that b equals -4/6 or -2/3. So if I do the same process but with a different value now, because now I have to find out what a equals, now I'm going to let x equal 5, because when I plug that in here, that's going to cause b to disappear because it's 0 times b. So plugging in a 5 for all the x's results in the equation 4 equals 6a, which means that a equals +2/3. So what happens now is the original problem now becomes an antiderivative of two smaller partial fractions. So it's the antiderivative of 2/3 over x minus 5 plus -2/3. That was our value for b over x plus 1. And then since there's multiple terms in that expression, you can find separate antiderivatives. And I'm going to go ahead and take these numerators out as coefficients. So the first one we can say 2/3 times the antiderivative of 1 over x minus 5. And then I'm going to pull out the -2/3 times the antiderivative of 1 over x plus 1. Now looking at this antiderivative, this is an example of du over u. And as I said before, the antiderivative of du over u is the natural log of u. So this is 2/3 times the natural log of the absolute value of x minus 5. And then here we've got a -2/3. This is another example of du over u. So that's going to become natural log of x plus 1. Alright, now a similar thing has to happen on question 5, where we're going to first just deal with this expression and trying to decompose it into its partial fractions. So the first step is to factor that denominator. So x minus 2, x minus 3. Again, since there are two factors, we're going to have two partial fractions. And as with the last problem, you would multiply the entire equation by the lowest common denominator, which results in the equation in a more simple form, or a form without fractions. 2x minus 3 equals a times, that's not a negative, a times x minus 3 plus b times x minus 2. And now choosing some convenient values, again, since we have one equation, but there's two different variables we're solving for, a and b, we've got to cancel one of the variables at a time. So if I first let x equal 3, And then remember, you got to plug it in for all these x's, all three of them. The equation turns into 2 times 3, which is 6. 6 minus 3 is 3, so we're going to have 3 equals, when I plug it in here, a disappears because 3 minus 3 is 0. When I plug it in here, we get 3 minus 2, which is 1. 1 times b is b. So right out of the bat, we get b equals 3. Now, using this, we can choose a convenient value of 2. When it's plugged in here, we get 2 times 2, which is 4. 4 minus 3 is 1. When it's plugged in here, we've got 2 minus 3 is negative 1 times a, so negative a. And then if it's plugged in there, b disappears because 2 minus 2 is 0. So we get 1 equals negative a, which means that a equals negative 1. So the original problem is the integral of partial fractions now. Negative 1 over x minus 2 plus 3 over x minus 3. And then we can separate into two antiderivative problems and then taking these numerators out as coefficients. So this could be negative 1 times the antiderivative, 1 over x minus 2, and then take the 3 out. And again, it's a du over u situation, which is natural log. So we have negative 1 times the natural log of absolute value x minus 2 plus 3 times the natural log of the absolute value of x minus 3 plus c. All right, question number 6 from the same section, 6.2 or 8.1 in the back of the 10th edition, UVU edition. We've got to factor that denominator. And looks like we're going to have a, let's try a 4 and a 3. Looks like 8x, yeah, that'll work. 2x plus 3 times x plus 4. Again, two factors in the denominator tells me we're going to have two partial fractions. And when we multiply the entire expression by the lowest common denominator, 2x plus 3 times x plus 4, if this is multiplied to each of those one at a time, we would have, on the very left side, the denominator would cancel out, leaving just the numerator 5x. With this, the 2x plus 3's would cancel, so a is left to multiply with x plus 4. And with this one, the x plus 4's would cancel, so b is left multiplying the 2x plus 3. So, as with the other two problems, let's choose a convenient value. Using that one, we could say let's let x equal negative 4. So when it's plugged in for all the x's, we're going to get negative 20. That's going to cancel the a, but here we're going to get negative 4 to negative 8. Negative 8 plus 3 is negative 5, so negative 5b. So b equals 4. Now with this one, we're going to let x equal negative 3/2. That's what it would take to cancel the b term for that x. So plugging it in there, we're going to have negative 15/2. Plugging it in here, we're going to have negative 3/2 plus 4, which is 8/2. So that turns into 5/2 times a, so 5/2 a. And then again the b would have disappeared. So trying to get a by itself, we can multiply by 2/5. And then the 2's cancel on the top and bottom. -15 divided by 5 is -3, so a equals -3. So coming up here, this turns into the antiderivative of separate partial fractions. And a, what was it? A was -3, so we've got -3 over 2x plus 3, and then what was b? B was 4 over x minus 4. So then we can separate this into two problems and then pull those numerators out as coefficients in front. So I'm going to have -3 times the antiderivative of 1 over 2x plus 3, and then a 4 times the antiderivative. Wait a minute, it's x plus 4. What am I doing? That's x plus 4 and x plus 4. There we go. Actually going to start with this one here, the 4 over antiderivative of 1 over x plus 4. That's again du over u, which a lot of them are, not every single time, but most of the time you end up with a du over u. So this is 4 times the natural log of x plus 4. Got to think a little bit more carefully about this one. Do we really have a situation of du over u? And the answer is no. If this is u, 2x plus 3, then du is 2. So to make this truly a du over u, we need to multiply this by 2, which means we got to divide out here by 2. So now we have it. So it's -3/2 times the natural log of absolute value of 2x plus 3 plus c. Alright, that finishes our problems from what we're calling 6.2, finding an antiderivative by using the technique of partial fractions. We skipped 6.3, we moved on to 6.4 in the book. We're talking about improper integrals. Improper integrals happens when one of the limits of integration is infinite, like this one. Or here, this on number 8, we've got the infinite one there from 0 to infinity. So an improper integral is asking you to find the area of a region where one of the bounds of integration is infinite. So it would appear that the region keeps growing. So you say, well, isn't the area also always growing? For some problems, though, the rate at which the area increases becomes so relatively small that you can actually find the area. We call that converging, using some formulas that you need to remember from this section. So what we have here with this, since the upper limit there is infinity, if you remember, and as always with integration, we don't want to leave a radical down there. So I'm going to go ahead and rewrite this as 1 to infinity of x to the -1/4. That's going to be a little bit easier to work with. So the trick here is to change this into an infinite limit. So the limit as b, we use the letter b if the upper bound is infinity. So as b approaches infinity, of the integral from 1, now instead of going from 1 to infinity, we're going from 1 to b of x -1/4. This is just the simple power rule. We need to add 1 to the power. So now let's take a look at the antiderivative. So if we have -1/4 and we add 1, that's going to be 3/4. So we've got x to the 3/4, and then we divide by it or multiply by 4/3. That's the antiderivative, but remember we need to now evaluate that fundamental theorem of calculus from 1 to b. So that's 4/3 times b to the 3/4 minus 4/3 times 1 to the 3/4. So we have the limit as b approaches infinity of 4/3 b to the 3/4 minus 4/3. So now we need to think what happens as b keeps getting larger and larger and larger. If you raise it to the 3/4 power, it still gets larger and larger and larger. And then if you multiply it by 4/3, it gets larger. So this just keeps increasing, increasing, and increasing without any kind of limit, without any bound. That behavior is what's called diverging. So this improper integral diverges. Okay, for number 8, we're going to again turn it into a limit problem. And since the upper limit or the upper bound there is infinity, we're going to use b. The limit as b approaches infinity. And then we're going to go from 0 to b now of e to negative 2x. So if you recall, the integral of e to the u du. If your exponent is u, then you got to make sure that you have the derivative of it in your expression. So if this is u, negative 2x, then the derivative is negative 2 dx. We've got the dx, we're missing the negative 2. So you got to have a negative 2 there, which means we need a negative 1/2 out there. So the limit as b approaches infinity, negative 1/2. Now the antiderivative of e to the u du is just e to the u. So it's e to the negative 2x. And then using the fundamental theorem of calculus, this is from 0 to b. So that's negative 1/2. And the b is just going to replace that x, but since we have that negative, I'm going to write this in the denominator as e to the 2b. Minus, now we need the antiderivative. The lower bound, so that's negative 1/2. And then if the 0 here replaces that x, we've got e to the 0, which is just 1. So really it's just to the negative 1/2 there. So what we've got to try to evaluate now is the limit as b approaches infinity of negative 1 over 2e to the 2b plus 1/2. So what happens when that value of b gets larger and larger and larger? Well, it's an exponent, so e to a bigger exponent, one that's getting bigger and bigger and bigger, e to that power keeps getting bigger and bigger and bigger. So what's happening here is the numerator is staying fixed. It's going to stay negative 1, but the denominator keeps growing and growing and growing. So the fraction is going to have a very, very large denominator but a small numerator, which means that the value of the fraction is actually getting smaller and smaller and smaller. If this happens to infinity, what ends up happening with this fraction is it goes to 0, leaving this value. So we can actually evaluate this expression as 0 plus 1/2, which equals 1/2. This behavior is called converging, so it converges to 1/2. Now, with this one, with the lower bound there, or the lower limit being negative infinity, we're still going to use a limit, but it's typical now to use the letter a, as a approaches negative infinity. Now we're going to go from a to negative 1 of x. I'm just going to move the exponent up so we can use the general power rule. And the antiderivative there is x to the negative 4 over negative 4. Now we're doing the theorem of calculus there from a to negative 1. So starting, you always start with the upper limit. So we're going to have negative 1 and then we're going to have okay. So the limit as a approaches negative infinity. Now with that expression there, since it has a negative exponent, I'm going to go ahead and bump that down to the denominator, leaving a 1 in the numerator, so it's 1 over negative 4 times negative 1 to the 4th, which is 1, so it's negative 1/4. And the same thing, since this one has a negative exponent, I'm going to go ahead and bump that one down, so it's 1 over negative 4 times a to the positive 4th power, and then here we've got negative infinity to the 4th power. So we've got a base that's getting larger and larger and larger, or more negative and more negative and more negative, but when it's raised to the 4th power, that just makes it positive. So that's growing and growing and growing. This denominator is getting very, very large, while the numerator is staying fixed. So we've got 1 over a very, very large number, a number that's getting larger and larger and larger. So like 1/10th, 1/100th, 1/1000th, 1/1,000,000th, 1/1,000,000,000th, those fractions are just getting smaller and smaller. So what happens as that continues indefinitely is this fraction becomes 0. And then we've got something that we can evaluate. We've got negative 1/4 minus 0, which is negative 1/4. So this converges to negative 1/4. Right, so the one section from Chapter 7 that we had time to do was Section 7.4, and it does seem a little out of place in this unit because we're reverting back to derivatives. This should have been done back in Unit 2, but we're squeezing it in. We've got partial derivatives of functions of several variables. We talked about this in class. A function of several variables represents a three-dimensional curve, or a three-dimensional surface, rather. So when you choose a point and try to find the slope of a tangent line on a surface, the question is which direction? Is it with respect to the x or with respect to the y? Because a tangent line in space can go in either direction. So there's two first partial derivatives, one with respect to x, one with respect to y, to give you which direction the tangent line is going to point. So we'll do both the first partial derivatives with respect to x and with respect to y. So the first one, f(x) of xy. So for finding the derivative with respect to x, what we're thinking of is y is a constant. Y is a number. Instead of a variable now, it's just treated as a number, like a coefficient. So what we would have is, for example, in this first part of the expression, if we just took the y out of it for a second, what's the derivative of x squared? Well, it's 2x. So now multiply it by the y that was there, and it's 2xy. So we've got 2xy. Same thing now, since we're taking the derivative with respect to x, we can say, okay, y is just a number, it's a constant. So what's the derivative of 3x? What's 3? And then 3 times the y that was there is 3y. The derivative of 2x is 2, and here the derivative of 5 and y are both constants, and the derivative of a constant is 0. So now the other partial derivative, or first partial derivative, is with respect to y. So what happens now is we hold x as a constant. So we take the derivative with respect to y. We're treating y as the variable, so we can take out the x expression. In this case, what's the derivative of y? Well, the derivative of y is 1, and then 1 times x squared is x squared. And here, if we take out the x expression, the derivative of y is 1, and then 1 times the x expression is 3x, so we've got 3x. Here, x is a constant, so the derivative of that is 0. And then here, the derivative of 5y is 5, so minus 5. Similar thing here on number 11, the first partial derivative with respect to x. We're going to have to use a chain rule since we have an inside function and an outside function. So the derivative of the outside function, the exponent just moves front, and the exponent decreases by 1. And then we have to multiply it by the derivative of the inside function. And since we're taking the derivative with respect to x, we can think about the y not being there for a minute. The derivative of x is 1, and then 1 times y is y. Here the derivative of 2x is 2, and then the derivative of 4y. With respect to x, remember y is just a number. 4 and y are both numbers, and the derivative of a number is 0, so it's y plus 2. Now the partial derivative with respect to y starts the same way. We have an inside and outside function, so decrease the exponent to 1, and then we need the derivative of the inside function. And this time we're taking the derivative of the inside function with respect to y, so we can think about this. All right, take out the x part of it. Now the derivative of y is 1, and then 1 times that x is x. With respect to y, that means the 2 and the x are both numbers, so the derivative of a number is 0, so that's gone. And the derivative there of 4y is 4. Number 12, z equals, it's the same as f of x comma y. It means the same thing, but it does have a different notation. The partial derivative of z, it's a funky looking d, and with respect to x is going to look like that. So partial derivative of z with respect to x. Remember the derivative of natural log is 1 over u du, so it's 1 over u times du, or the derivative of our denominator. First time around we're doing with respect to x, so the derivative of 5x is 5, and the derivative of 4y, again thinking of 4 and y as just numbers, the derivative of a number is 0, so it's just 5 there. Now the partial derivative of z with respect to y, same rule, the derivative of natural log is 1 over u times du. This time around, the inside function there, we're taking it with respect to y, so 5x, x is just a number, and the derivative of a number is 0, so that's gone. Derivative of 4y is 4. And that's about the extent of what we did in 7.4, is just practice finding the first partial derivatives with respect to x and y. The rest of this exam review is more of a practice for students to not just practice integration techniques, but deciding which technique to use. Is it going to be the general power rule u to the n du? Is it going to be the integral of du over u? Is it going to be the integral of e to the u? Or is it going to be derivative or integration by parts, which is the integral of u dv? So something there that's going to have to be decided. Now what I'm seeing here in question 13 is we have an expression e to the u. So e to the u du maybe, is this something that could work? Well, what we got to test then, well, if this is u, then du is 9x squared dx. So we've got the e to the u, but what we don't have is the du. We've got the x squared and the dx, but we're supposed to have a 9 instead of that 45. But luckily 45 is a multiple of 9, so we can pull out a 5 and call it 9x squared. And then we'll be able to write this as 5, and then this just gets replaced with e to the u, and then the 9x squared dx gets replaced with du. And if you remember, because I hope you do, this is an easy one to remember, the integral of e to the u is just e to the u. So the antiderivative is 5 e to the u plus c, or 5 e to the 3x cubed minus 4 plus c. For 14, looks very similar. We do have an expression involving e, so is this going to be one where we can do e to the u du? Well, what happens is, okay, well, if we let that equal u, then du is 3 dx, and the problem is we have an x squared there that we can't really account for. So this whole u and du and e to the u didn't work. We do recognize though that this is a product. We have one factor here and one factor here, so it's something times something. And one of those products involve, one of those factors of the product involve e to a power. That's often a telltale sign of integration by parts. So what we're going to have to do here is say, all right, we're going to have u dv, and then we can write this as u v minus the integral of v du. This is the actual rule we're going to use here. So we've got to choose which one's u and which one's dv from the original expression. Remember, u is the expression whose derivative is more simple. So I'm going to say that u is equal to x squared. So then du is 2x. 2x is considered more simple because it is a degree less. So 2x dx. So that means dv is e to the 3x. Well, that means v is the antiderivative of that. So v is the antiderivative of e to the 3x. Now we can only find this antiderivative e to the 3x if there's a 3 there, which means there has to be a 1/3 here. So the antiderivative is 1/3, and here the antiderivative of 3e to the 3x is just e to the 3x. So there's your value for v. We've got our value for dv. We have our values for u and du here. So the original problem, x squared e to the 3x is u times v. So x squared times 1/3 e to the 3x minus the integral of v, which is, it's got a coefficient which I always pull out front. So e to the 3x times du. Now du is 2x dx. Now we have another slight problem. This antiderivative is not going to be quite so easy to find. Reason being is, all right, we have e to the u, but then this right here is not du. 2x is not the derivative of 3x. So unfortunately, this antiderivative is going to require its own little integration by parts. So we need to choose a u and a dv. But luckily from the problem that we just did, right here, we know that the antiderivative of e to the 3x is 1/3 e to the 3x. So this becomes u times v minus the integral of v times du. And then actually the 2, this 2 doesn't really need to be there. I'm going to go ahead and pull that 2 out in front and call it 2/3 and then just leave the dx there. So this is, I'm just simplifying this, 2x times 1/3 is 2/3 x e to the 3x minus, now the antiderivative, again this is the third time now we've done it, the antiderivative of e to the 3x is 1/3 e to the 3x. So we've got 2/3 times 1/3 e to the 3x. So now this expression, the antiderivative, remember from right here there was a 1/3 in front of that, and then the rest of it we had that in front of it, so minus the 1/3 times x squared there is just x squared over 3 times e to the 3x. So we have x squared over 3 e to the 3x minus 2/9 x e to the 3x, and then this 1/3 multiplies there to make another 2/9, so plus 2/9. Actually, that makes 2/9 there, which multiplied with another 1/3 makes 2/27 e to the 3x plus c. Wow. Okay. Well, that was fun. Hopefully we end up with a few easier ones here. It looks like, right off the bat, what I'm noticing here, if I want to let that equal u, then the denominator is just du. So this is kind of a nice one. We've got du over u. So this is just, we don't even have to multiply by a coefficient or anything. This is just du over u, which is the natural log of u. So we've got the natural log of 2x squared minus 1 plus c. Oh good, thank you, an easy one. You're welcome. Now 16, we have an inside function and an outside function there. So often when there's inside functions and outside functions, we try to use the general power rule, u to the n. U to the n du, which isn't in the form of a fraction. This one is in the form of a fraction, so it would help if we move this denominator up to the numerator using a negative exponent. So 6x squared x cubed minus 3 to the negative third. So the inside part will be u. Du is 3x squared dx. So we've got the x squared and the dx, but it's supposed to be a 3, and we got a 6 there. But again, 6 is a multiple of 3. So if I pull out a 2 in front, then that 6 does become a 3. So then this inside part becomes u, and then 3x squared dx becomes du. So this is 2 times u to the negative third du, and if we apply the general power rule, and then the 2's would cancel, so we'd have negative u to the negative 2, so, or negative 1 over u squared Number 17, it is typical or common when you have a product, something times something, and one of the factors of that product is a natural log. It is typical that we use integration by parts, and usually you let the natural log part of it be your u value. So u equals natural log du with 1 over x. So then the remaining piece there, x squared, is your dv, and then the v is the antiderivative of that, which is x cubed over 3. So we've got all the pieces. So we've got u and our dv. So the antiderivative of u times dv is u times v. Minus the integral of v, and this x cubed over 3 is really just 1/3 x cubed, so I'm going to pull the 1/3 and then have the x cubed, and then times, so we've got our v times du. Du was 1 over x dx, and then x cubed times 1 over x is just x squared, so this is natural log of x times x cubed over 3 minus 1/3 times the antiderivative of x squared. And the antiderivative of x squared is another x cubed over 3. So the final answer here is there we go. So we recognize on number 18 that we have an inside function and an outside function. So what we're hoping is that what's left over is in some form the derivative of this inside function. So if we let u equal the inside function, then its derivative 15x squared. So we've got the x squared and the dx. There's supposed to be a 15, but we got a 30. But we can change that 30 into 15 by taking out a 2. So now we've got u to the 5th, and then that's du, 15x squared dx. So we can write this as 2 times the antiderivative of u to the 5th du. So the antiderivative of u to the fifth is u to the 6 over 6, and then the 2 over 6 there is 1/3, so we've got u to the 6 over 3. So we've got 5x cubed plus 3 to the 6th power over 3 plus c. Number 19, we can't really move this numerator or the denominator up to the numerator using any kind of negative or positive exponent, so we're not going to have u to the n, and we're thinking, all right, well, maybe it's du over, is this du over u maybe? Because if it is, we can use natural logs. Well, if this is u, then the derivative is 2x plus 2, which is not the same as what we have there. So du over u isn't going to work. So the other thing we learned is if it is in the form of a fraction and we can't do du over u, or we can't move the denominator up to the numerator, then we could explore partial fractions. We can decompose it into partial fractions like we did in section 6.2 or 8.1. So if we factor 2 factors in the denominator means 2 partial fractions. And then if we multiply that expression by the lowest common denominator, and then it multiplies each of those. When it multiplies over here, the denominator is going to cancel with the LCD, leaving the numerator 7x plus 1. When it multiplies the a partial fraction, the x plus 3's cancel, leaving a to multiply with the x minus 1. And when it multiplies the b partial fraction, the x minus 1's would cancel, leaving b to multiply the x plus 3. So now we have one equation, but to solve for 2 variables it doesn't work, so we need to cancel one of the variables at a time. I'm talking about a and b as the variables. X is not the variable here that we're solving for, so we can let x equal whatever we want. Using this, for example, we could let x equal 1, and then a would disappear because 1 minus 1 is 0. So if we let x, all the x's in this equation equal 1, then over here we have 7 times 1 plus 1, which is 8. A disappears because 1 minus 1 is 0, and then for b we get 1 plus 3, which is 4. 4 times b is 4b. So b, rather, equals 2. And then using this, we could let x equal -3, because then that'll cancel out the b part of this, allowing us to solve for a. So if all the x's equal 3, then over here 7 times -3 is -21 plus 1 is -20. And then here we get -3 minus 1 is -4a. And then we already decided b would cancel because -3 plus 3 is 0. So solving this now, we get a equals 5. So coming back up here, the problem turns into the antiderivative of partial fractions, 5 over x plus 3, and 2 over x minus 1. And like the problems we did earlier in this review, we can separate this into 2 antiderivative problems and at the same time take those numerators out as coefficients. So 5 times antiderivative x plus 3, and then 2 antiderivative of 1 over x minus 1. And then both of these are just du over u situations, which is natural log. So we have 5 times the natural log of x plus 3 plus 2 times the natural log of x minus 1. All right, last but not least, number 20. In chapter 2 and 3, we talked about derivatives. In chapter 3 specifically, maybe it's chapter 4, we learned the derivative of natural log. is 1 over x, but we have never really talked about what the antiderivative of natural log is. It's because there's no formula for it. So right now we're going to find the antiderivative of natural log using brute force and integration by parts. Integration by parts means we need a u and a dv, and then we could use uv minus integral of v du. We don't have much to choose from. We've got natural log of x and we've got dx. Those are the two choices. And remember, it's typical with integration by parts, the natural log part of it is your u, and then that means this is our dv. So u equals natural log x du, then is 1 over x. If dv is equal to 1 dx, the antiderivative of 1 is x, so v equals x. So the antiderivative of natural log of x equals u times v, so and then that's multiplied. So there's u times v minus the integral of v times du, and then here x times 1 over x is just 1. So we've got, I'm going to write this a little bit differently. We've got x times the natural log of x minus the antiderivative of dx, and that's x times the natural log of x minus, now the antiderivative of 1 dx, the antiderivative of 1 is x, so we've got minus x plus c. And there you have it. You guys made it. Way to go.